very happy to be here. I was here in Darmstadt in 2008, and since then I've never been back. So I'm very happy to be here, and very happy to have this opportunity to talk about some of the things that I've been thinking about for years. So the title of the talk is How to Make Machines That Adapt Quickly. And the answer, I don't really know, but I know how to get there. So that's something that we have figured out. And I'm going to try to share that experience with you on how we can go down this path and make this really happen in the next few years. So I've been very fascinated with this question for a long time, but it really kind of clicked to me when I have my first child. So this is my daughter. She was at 6 months old at the time. And you see that she's trying to kind of learn about the world, this ukulele world, and some things are more interesting, other things are not that much. She's slowly figuring out that she likes the sound of this thing. And if you give her enough time, so this is after 6 months, she has converged, or sort of converged, so she knows something about the world, that she's able to get the sound that she likes. So she knows that she likes some sound, not the other things around it. This is very fascinating to see how kids can slowly, figure out things. And it's also true for us. Every day we live our life and we kind of see more data, more experience, and then we know more about the world, and we feel that we have figured out some things what we want to do in the future. But we don't really stop in this, right? We take our past knowledge, and when the environment changes from a small instrument to a bigger instrument, we can still, again, adapt our skills, our previous knowledge to get the same experience that we love about the world. Right? This is remarkable. And then when I think about in machine learning, what we have, well, we're nowhere close to any of this is what I think, right? So this is an older slide, but actually not much has changed since 2016. This is a Microsoft product which was put online. It's a bot supposed to learn from the tweets of other people, but in just 24 hours, it started saying some really hateful things that are not acceptable. So people kind of tricked it very quickly. So in this case, the system adapted too quickly. It started looking at the data that it just got in the last 24 hours, and it forgot the knowledge that it had before. So here, the adaptation was too quick. But there could be some other problem that sometimes system is too rigid. It's too slow to adapt by construction, right? We don't see these videos. We only see them dancing and doing amazing, cool things. But this is the reality of robotics. So the system is too slow to adapt. So in general, there's this tension between the past and the future. And we have to somehow put our old knowledge together with the things that we are seeing right now and what's going to happen in the future. And machines are extremely bad at this. So this is what I want to convince you today, that this is actually a problem that large language models, I have to say ChatGPT once at least in my talk. So ChatGPTs are not going to solve this problem, is what I'm saying. Right now, if we need to do something, I think the first speaker talked about this, if we want to change some knowledge in the model, we don't have a way to slice things and add some particular things or remove some knowledge from it. So any small change that you want to do, you don't have mechanisms to do it, and you just have to retrain things, right? So we have, an AI system that works extremely well, but requires this ridiculous amount of resources. There's a reason for it, because this is what we can make it to work. We can have a large amount of data at the same time, and then we can do some magic on it, and things seems to work. But we don't know how to add and subtract and take things out of the model or adapt it just slightly to our purpose. Fine-tuning doesn't really does it. Let me add that. So this is one of the reasons why I think we don't see this kind of breakthrough in some of the places where we really need AI to be doing things. So like robotics, in medicine, in climate change. These are more dynamic settings. Things change on day-to-day basis. And we want the model to be adapting to these things, and this is just really hard right now. Okay, so my goal has been to kind of solve these challenges, make a system that can adapt, at least understand when you can adapt quickly, when it will take you a long time to adapt, so that you can go back to retraining your system. But with that, I also feel that if you solve this problem, I think you bring back principle to deep learning. You take this magic out. We think that everything works, anything is possible right now. I could do anything. But this is not true. There's no magic. We shouldn't believe in magic. So with this work, I think it is possible for us to kind of do more science and reduce this magic and religion from it. Okay, so with that, I put the proposal for today's talk, and my talk is just too long, unfortunately. So I'll have to kind of cut down things and not talk about too many details. I wanted to give the complete picture of what we're doing, and I just ended up having too many things here. So I'll skip some things, but the general kind of outline is that we'll start with something Bayesian, because that's one way that we can unify, generalize, and improve things. So I'll propose an algorithm called Bayesian learning rule that will explain a lot of deep learning algorithms that are working well. It will highlight why they're working well, perhaps, because they are all optimizing a similar Bayesian kind of objective. And then this will allow us to understand what the algorithm remembers from the past. So you can kind of go inside the brain of the algorithm, and you can remove certain things from there and understand certain things that are very crucial for the algorithm to work well. So you go into memory, and this sensitivity and duality will use that of this Bayesian learning rule that I'll present. So once we understand the past, then we'll think about how can we modify it? How can we adapt the past to the future that's coming? And that will shed some light on why some problems are going to be easy, other problems are going to be hard. Right? So in the end, if you don't remember any of the details and the Bayesian stuff gets in the way of you to kind of understand or appreciate this stuff, just remember that to adapt quickly, things are easier when the past is not going to interfere too much with the future. That's kind of the layman summary of the talk. So I'll try to write math that will show you this. Okay, so let me start with the first part of the talk. We try to bring back principles into deep learning, try to take all these different kind of algorithm and see them from the same common principle. And the question that we were asking a long time ago on this is similar to this question of origin of species. So what are some of the common origins of the artificial algorithms that we use? Right? We hope that the algorithms that are working well in practice, like SGD, RMS-prop, ADAM, and maybe other message passing stuff and other things that people use in Bayesian field, there should be something common between them. Maybe they're all optimizing the same objective, and maybe the way that they optimize this objective is also similar. So what are some of those things? We wanted to figure it out. So with that, we proposed this algorithm that I call Bayesian learning rule. So it's a sort of an extension of Bayes rule, where we argue that if you take a Bayesian objective and make two changes in it, you can recover all sorts of algorithms. So in this first column, okay, my cursor is not there. Okay, maybe, can I get the pointer? Yeah. Sorry, so the first column in there, I got it. In here, I have all sorts of algorithms. So from optimization, gradient descent, Newton's method, from deep learning, RMS-prop, SGD, all sorts of things, lots of Bayesian stuff. What the claim is that you do two things. You change the approximation to the posterior. They're mostly going to be like Gaussian or some variants of this with Bernoulli, some things like that, some exponential family approximation. You choose this. And then you use something called natural gradient. You don't really have to know this, but it's a special kind of gradient. And you make some approximations to it. And with this, you are able to explain all of these algorithms. So you have one rule. If you make these two choices, you're able to reduce it to the learning algorithm that is listed in the first thing. But then the second point was that now that I have made the approximation, how do I know that I made the right choices to show this? Maybe I'm just fooling myself. So then we try to relax this approximation and make new algorithms. And the hope is that when you relax the approximation, it should work better. Then it justifies the approximation. So talk about this particular thing that we do. It's an online Gauss-Newton method, a Bayesian version of it. I won't go too much into the math, but first show you the, wow. I think maybe we don't like uncertainty, so you can't see the uncertainty here, in this projector. But you'll have to just trust me now. So this is a classification problem. This is Adam. Was it find a good classifier? And if you use Bayesian learning rules, so these two papers, this is a while ago, you get this line, but you also get uncertainty around it, which you cannot see right now. But I'm showing a lot of samples, like you can maybe see a hint of it. So it's trying to fill up the space where you haven't seen the data. So it's kind of figure out, it's telling you that there's no one single line that is a good classifier, but you can also draw a classifier like this or some things like this. Okay, so there's a distribution over these lines that we must be thinking about, not just one single line, because there's no one good answer to it. So the nice thing that we try to show with the Bayesian learning rule that if you, so I haven't shown you the detail, but I'll just show you first the example. So RMS prop, maybe most of you know, you take the gradient, you compute some kind of scale vector, then you take the gradient step. So you multiply by some preconditioner and you update your parameter. So if you use Bayesian learning rule with a Gaussian distribution, you get pretty much the same algorithm, almost line by line. But now we're going to try to improve this by adding uncertainty to it. So we want some variation in our classifier because we haven't seen data everywhere. So for that, we make these changes that are shown in red. And it's really, really small changes. And it turns out that this preconditioner that you have here is related to uncertainty. So if you think about it a little bit more, it's quite nice because the uncertainty affects the step size. So it tells you how fast or slow you should be learning. This is very, very natural. People in neuroscience have actually worked on this quite a lot also. So this was one kind of sign that we were doing something right. So this is more general formulation here I've shown, like how that algorithm come out to be. Essentially, in deep learning, you minimize this, and I'm saying that we shouldn't minimize for just one line, so like one parameter in that blue line, like what Adam will find. We should be doing something like a Bayesian thing where we have a distribution. So think of it like a Gaussian distribution with a mean and the variance. So we're learning both the mean and the variance. We're learning that red line and some variance around it. And to have the variance not be zero, I add an entropy term. So it's somehow helping me to explore around the mean that I have. And the second point that we say, so our hypothesis is that all of these good algorithms are optimizing something like this, and they're optimizing using a special algorithm. And I don't have time to go into the detail of this today, but you should just remember that it's something like natural gradient descent or equivalently mirror descent, which we are using to learn the parameter of this Gaussian or distribution. So here I've written this with lambda. So lambda is the natural parameterization. That's all you need to remember. So think of it as like some function of mean and the variance. It has like two parts to it. It includes both the mean and the variance, and we are trying to learn it. And we are learning it by taking the gradient of this, but we're not taking the gradient with respect to lambda, but some other parameter. So not going too much into the detail, but you can see that in the paper. But the main point here is that if you're an optimization person and you think it's just mirror descent and you know what it's doing, I will encourage you to read the paper because it's not just that. There's a very special thing here with entropy that's going on. So it does lots of amazing things, and that's why we are able to recover existing algorithms from it. If you have heard of natural gradient descent and you think what's going on, I will again encourage you to read the paper because it's really unique. It's not the natural gradient that you know. Okay, so with that, I'll just kind of end it. I'm not giving too many details here, but the main idea here is that we're trying to take the posterior, right, this Q, and we're using its information geometry somewhere when we compute this gradient. there's somehow a fissure involved here. And that is what makes it all possible. Okay, so that's the main kind of point here. Okay, so with that, that was the thing. So you take that rule and you then kind of plug in a Gaussian, you do some simplification. All that math then gives you this picture that I showed you, and the algorithm is called online Gauss-Newton method. And it gives you this line, but also it gives you the variance that you cannot really see in this projector, but you have many lines that you can sample from your Gaussian. Okay? And at the time, so this was like 2019, this was the first algorithm from the Bayesian world that actually could compete with Adam. So it gave, so this is on ImageNet. It gave almost the same performance as Adam, but its uncertainty estimate was much, much, much better. So that was kind of a very nice thing for us to get. Of course, this is not billion parameters, and it's no ChatGPT, but what we started with science, it actually works. And then we had further confirmation on this. So one of our students actually did another nice modification of it, just kind of adding another term to it, and really computing not Gauss-Newton, but computing the Hessian properly with a reparameterization trick. And this one got the first prize in the NeurIFS challenge without really not much work. We did very little kind of tuning and stuff, and it just worked out of the box. So this was done by the members of the group and somebody from TU Munich. And with this, you can do kind of, I just have to show this picture. So you could do this. It's not too costly. It's the same cost as Adam. There's no additional thing. Maybe you have a mental block because it has a word Bayesian in it, so you don't want to use it, but that's another story. Okay? So you could do all sorts of things. Okay. So, so maybe I'll show you one more thing that has recently happened. So all this Bayesian principle actually really explains a lot of things that are working well in deep learning. So this is another algorithm called SAM, Sharpness Aware Minimization. And people say it works well because it finds flat minima, whatever that may mean. It's somehow flat, right? So the way that it actually works, or at least the paper starts with this. I don't think they really do it. But let's say you're at this place and you want to go here. You kind of draw a circle around you, and you say, I don't want to trust this place. I want to look at the worst possible loss. So you go opposite direction. The loss is increasing in this side. So I do supermum over this perturbation. Right? So this is kind of like, it's nice because it's looking not just at one point, but it's looking at the neighborhood of what could go wrong in this neighborhood. So this is somehow aware of the sharpness of the loss landscape. But actually, when you write down the Bayesian objective that I showed you before, we had an expected loss there, right? So if you do some math, kind of rewrite, try to bring these two things in the same kind of place, you see that it's actually also doing very similar things. So this is looking at the maximum, like the worst loss, but this one is looking at the average loss. Okay? So this adversarial versus average case has been actually known in statistics for a very, very long time. These two things do very different things, but they're both kind of looking in the neighborhood. They're both drawing a circle. One is drawing with a hacky parameter rho, and this one is drawing with the posterior variance, is the uncertainty. And it's drawing that circle. So somehow there should be some connection between the two, is what we thought. And if we do some work on this, we're able to show that actually it turns out, well, it's a fancy word here, but it turns out that this is the best convex relaxation of this guy. Okay? So the average and the worst case, they're related through this kind of convex relaxation. So this is an optimal convex relaxation of this. Now this connection to base then helps us to do all sorts of things. So because now we know that the circle that you draw is related to the confidence, it's related to the uncertainty, somehow related to sigma. So then we can sort of try to show that, okay, if you do some kind of Bayesian thing, actually you're smoothing out some local minima. So this gray line is the loss function, and the blue line is the expected loss. And what happens is, as you increase the variance, it sort of smooths these smaller, insignificant local minima. but keeps the more dominant one around. Okay? And you can show that SAM is actually always finding an upper bound. So the star is the max loss, and it's always above the blue thing. Okay? So it's quite nice, and it tells us that actually we can also extract uncertainty from SAM. So this is kind of what we did, is we did the same kind of math. You write down SAM with RMS prop. It adds these two lines in RMS prop. And then you write the Bayesian version of it, and it's really line by line, it's the same. And it's really beautiful math. You start from the Bayesian learning rule, you apply these things very mechanically, and you get these updates where you change some of the things, and you get the variance. It's the same story that the step size, the learning rate is somehow modified by the preconditioner, by the uncertainty. It's what we would expect to happen. So not only this, if you look at the performance, well, I have to show this, but this is less important. We improve some performance on some things, about 10%. On fairly large things, I don't know, it's not billion parameters, but okay. So with that, this is the first part about unifying, generalizing, and improving. And I know it's after lunch, and it's so this is second part we're starting, but I hope you're still with me, and we're going to change things a little bit and get towards adaptation. So now we have put everything together. Hopefully, we are convinced that maybe the Bayesian thing is worth considering. It has some value to it. So now I'm going to try to go into the next step to say the same algorithm that I showed you in the previous slide also helps me understand what an algorithm remembers, what matters to it. Okay? So what is relevant from the past? And we're going to try to look into this, and we start thinking about it from really first principles. Okay? So if you have a system that has many parts in it, and you want to understand why does the system work, then what you can actually do, you can go and you can try to perturb certain parts. You may try to stop certain parts. And if it affects the functioning of the system in a major way, you know that that part is crucial. Right? This is a very simple perturbation analysis. It's fundamental in many, many fields. Okay? So we're going to try to do something like this. We'll perturb something, we'll measure the sensitivity, and somehow this gives us a dual representation. It's an alternate representation that works in the sensitivity of things. Okay? Now, before telling you how Bayesian learning rule makes this possible, it is very, very surprising and unexpected. Let me first give you a use case of what we have done already with it. So this paper is under review for some time, but we call this memory maps, and it's really just taking the Bayesian learning rule and reading certain natural gradients from it, and it helps us to understand generic machine learning models and algorithms. So here's an example. What I'm showing you here in y-axis is prediction error, x-axis is some kind of uncertainty estimates that's derived from this sigma square that I've showed you before. And every dot here is a data example. Okay, so it's kind of a scatter plot. And I'm also showing you histogram, meaning that most of these data examples lie somewhere here, and this is only the tail that you're seeing. Now, if you go inside and so these quantities are taken from Bayesian learning rule. I'll show you how in the next slide. But let's first see what we get. So if we zoom in here in this part, so we look at these points that are here, you see, so these are put in the row with different classes, so 0, 1, 2, 3, until 9. And you see that these are all regular example. They're like regular Joes, just doing their thing. So this is the majority. But then if you go in the tails and you start to look into what's going on at these places, if you go in the y-axis, you look inside the red box, you see points that are difficult to predict somehow, because the prediction error is high, right? So you see a 1 that's kind of look like 7, maybe 7 that's labeled as 1, maybe they're mislabeled. Some of these 3s are 5s and 9s, actually, so they're mislabeled 1 on this side. So they have high prediction error but low uncertainty. But if you go here and you see points here, these have high uncertainty but low prediction error, lower prediction error. If you look at them, they look weird. So this is like 1, but they're all very different. 1, 2, but they're very weird-looking things. Right? I hope you get an idea of what's going on in this memory map. It is somehow encoding how the model sees the data. Right? These think that it's able to predict well with high certainty. It's very confident about it. They are very regular-looking digits. But the ones that are in the tail are more interesting cases. The weirdos are all here. Right? So these are maybe mislabeled, difficult to predict for some other reason, and maybe they have, they're ambiguous examples because they're kind of varying here and there quite a lot. So this is very revealing of what's actually going on in the system. And I'll tell you what to do with this later, but let me first give you a very quick glimpse on how this is actually done. So we are actually looking into the loss function. We go inside, so the brain that I showed you before, what it's made up of is all these data examples. So there are n data examples. There's one regularizer that I denote with 0. So there's n plus 1 terms here. They all make up the loss function. And that's how a model is kind of come out of there. So what we're going to do is we're going to look into characteristics of each of this loss function. And essentially, it's very simple. I've written the Bayesian learning rule in a slightly different form. The entropy disappeared. It becomes this in this case. But let's not worry about that. The more important thing is that now my natural gradient is summed over all the data examples. Okay? And that is what kind of is the thing that is important. So you could do this during iteration, but I'll just show, let's say when it converges, I know it's hard to do the calculation, but just believe me that when it converges, it looks like this, that lambda is equal to the sum over all of these things, and then this is the natural gradient of each of this loss. Okay? Now, here's the important thing. So this guy is the overall Gaussian, is the global natural parameter, is the mean and the variance of the big Gaussian over the parameter. And this shows you that it's made up of small contribution from each data example. So every data example is adding something to this. Right? So it's very easy to kind of see from here that if this guy, this natural gradient of the ith example is very big, then it contributes quite a lot to the posterior. And this is kind of the idea. This is related to duality, and I'm not going to go in that and bore you about this, but there are some relations to Lagrange multipliers and some perturbation things that it helps us to do all of these things. When you remove this, how much this will change, this helps you to understand if the thing is very sensitive or not. Okay? But the main contribution of this work is that we can do this during training. So you could take SGD iteration, you could take RMS prop iteration, you could take Adam iteration, and you can apply this theory to them because they're all sort of doing the same natural gradient iteration as I showed you before. Okay? So with that, the math is almost over. So now let's look at some pretty pictures. And I hope this made sense to you, but if it didn't, just think about like something like sensitivity that we're going to do. Okay? Okay, sorry. So now the question, so we're going to do some kind of perturbation of the memory. So we have the memory map. We know how each data point contributes to it. And now we're going to try to remove some of the examples. We call it perturbation, so memory perturbation. And the question is, how sensitive is a model to its training data? We're going to do it through this. And turns out when you do this calculation, and it's a few lines of math, it's not very complicated. When you remove this natural gradient for one example, you can show that the deviation of the model, like how much the model is going to change, it depends on how high prediction error you have and how high uncertainty you have. So the two axes that we had in the memory map are essentially what is contributing to it. How much time do I have? 5 minutes left. I have 5 minutes left? Okay. Here I'm seeing something different, but okay. My talk is 45 minutes, right? Including questions. Okay, so 10 minutes for question and okay. All right, I'll have to speed up. Okay. Okay. So I'll just show maybe like one or two examples and go to continual learning, and then we'll end this. So here, it's kind of an illustration of how this thing works. So you have an old model, and let's say you add a new data example to it. Okay? And if the data example is very close to the old thing, the model doesn't change much. But if the data is far, the model changes a lot. Okay? And that makes sense. Now, this equation is essentially kind of making this observation more mathematical. It's saying that if the observation is far from the old data, it's harder to predict, then the changes are going to be large. If the model, if the data point is also such that the model is uncertain about it, or somehow ambiguous, then also the model deviation is going to be hard. Okay, so this is kind of telling you what examples are important for a model. Okay, now with this, sorry, I forgot to tell you, but this was actually originally done in 1977. But what we do now kind of generalizes this really to almost everything that you can think of. Everything that's covered under a Bayesian learning rule can be done in the same way. You can derive this same equation using what we have actually done. Okay, so with this, now you can do a lot of things. So you can sort of understand the memory of the model, right? So you have this kind of memory map. You can go inside, and you can look into different regions. You can analyze examples, and that helps you to understand what the model is actually doing. You can also do other things, like you can try to understand the complexity, and you can observe the simple model usually are on this side, then complex model kind of go on this side, so their uncertainty is kind of higher. But the prediction error is lower, and this 2D illustration kind of tells you how these things work. So you can figure out the overfitting of the model. You can apply this to anything. So you can do this for Bayesian logistic regression, for support vector machine, for neural network, for Gaussian process. You can figure out what examples this model finds relevant. And you can compare them. So you could see logistic regression, very rigid model. So it's not really learning the pattern. So different points matter. But neural network and SVM, they're doing something similar. But then Gaussian process is also learning points on this side because it cares about uncertainty. Right? So there's some nice things that you can understand with this. And this is my favorite plot. What we can do, and I didn't really think that this would be possible, a few years ago. I couldn't believe myself. But you can also predict generalization during training. So this is basically showing an training trajectory. This gray line is the test data. So it's the actual test data. And the black line is the training data. So I've used no test data in this black line. But essentially what I have computed is I have tried to remove data example from the model. So the removed data example acts as a test set. So it's like kind of leave one out kind of test. Okay? But it's really, really faithful. And this really works in lots of cases. And you can also do this with plain Adam. This one, we used the Vaughan-like algorithm, the BLR thing. Okay. You can also remove the whole class and predict what will happen without retraining. Okay, so the x-axis is the true performance, y-axis is the estimate, and they really, so I'm removing like class number 9 and see what will happen, things like that for 2 models. And you really see that you don't have to retrain, you can understand the model beforehand. Okay, how much time do I have now? 2 minutes. Okay, I'm going to take 5, if that's okay. Huh? Because I have to close the loop, right? So I would have actually finished the talk right now, but this is the first time that I'm trying to tell the full story, and I know that people here in the audience care about this question. So how do we use all of this to do adaptation, right? So now this is really putting this to good use, and I'm going to skip this, but deep learning does this, and we want to do continual learning where we don't forget the past. So we did this some years ago where the first time we come up with this idea of memory, we used to call it memorable example at the time. This is 2020. Yes. And at that time, we made a system that does continual learning like this. So let's say you observe the data, you got this line, you find this memorable example. This is basically the memory, the highly sensitive example. At the time, we didn't know what we were doing, but we have some idea that this should kind of work. So we pick these things and we freeze them. And then when we observe the next set of data, we try to not lose performance on this old data. So that's how you're kind of avoiding the forgetting of the past, okay? And then you repeat, you store some things in memory, and then you get the new task, and you continue like this, okay? So that's, I hope you get the idea. Okay, so we didn't really know why it was working well, and at that time, so there's this method that people use, this kind of weight regularization, making sure that your new parameters are same as the old parameters. And this very well-known paper from DeepMind. But what we were actually doing was more of a functional regularizer. So you can think of like, it's not thinking about the parameter, but it's thinking about what the model does. So it should be functionally somehow be similar. And we had this kind of regularizer. At the time, we didn't really understand. But actually, if you look inside this, it has two parts to it. You know, these are two axes of the memory map, okay? Which is extremely beautiful now looking back at it after many years. So this kind of is saying the predictions should match, okay? So sigmoid is the softmax function, and f is the function output of the old parameter, old model. So old model, new model should be matching things, okay? Makes sense. And somehow the uncertainty should weigh them. So the uncertainty of those examples is also important, okay? So this was already there in the old thing, and then we did all this other work, so 2-3 years we took to understand why it actually works, okay? So now we have the answer, but we don't have the time to tell you, okay? So it's really just back to memory map, right? So the very simple answer is that you have two axes, and both of this will contribute to adaptation. And if you have many examples here, you're in trouble, okay? So you need to think about the sensitivity of your algorithm and how it's going to interact with the future. And if the future looks very different from the present, it'll take you a long time to adapt. If the future is similar, I mean, I'm not telling you anything new, but I have math now to explain this, okay? So that's, I feel satisfied with this. So if you want, you know, if I'm proud of one work in my life, this is the paper, but I'm sure you will go read it and it will make no sense to you right now. So next 5 years, I'll be explaining this. You know, this is my job now. So basically why these things actually work is because we should be measuring things in the parameter space and also in the functional space. And this is really a very simple answer. And we can explain all sorts of adaptation methods, starting from, you know, least squares to SVM to things that are happening in deep learning right now, and knowledge distillation. All of these things can be written in this form. So why these things are working well is the reason that they are actually doing this kind of comparison, okay? So with that, I will not go into showing you, you know, how we can beat things. So you shouldn't do replay. You should use memory of some kind and all that. And we have some results on ImageNet. We don't have time for that. But let me just close the talk. So is it okay? Good. Okay. So I showed you first that, you know, deep learning is magic, and we don't want magic. So I work a lot in bringing everything down to the same principle. So the hypothesis that all of these good algorithms are optimizing a Bayesian objective, and somehow that helps us to understand why they're working well. And then we can go inside and look into what they have actually learned about the data, so what kind of memory they have. And then we can use this memory to understand when can they be changed without retraining from scratch. So how can they be quickly adapted? So we've been very lucky. So, you know, I'm not really into beating, you know, a bunch of benchmarks, numbers, and all that. But my goal is to start a new field about thinking, you know, how to design this kind of adaptive system that are robust, that learn continuously. So we're trying to push for this Bayes duality project, which is really about trying to understand models and algorithms using some kind of duality. We also have a workshop at ICML, so if you're in Hawaii, please drop by there. And we are very lucky to have some money, so we're secure for a few years. With that, I'll close this with a lot of thanks to lots of people in the group and lots of people whose pictures are not here. So thanks a lot, and thanks for listening.
thanks a lot for this inspiring talk on the advantages of Bayesian learning. I think we still have time for 1 or 2 questions, short ones, if there is someone from the audience. Just raise there.
Empty, super cool talk. Just 2 questions. One is there relations to functional gradient boosting then? Because what I see is somehow that you make use of a ensemble view of a single model, and then you say, okay, let's not only look at the weight, but also at the function space. And so I think we can maybe go for a fully non-parametric view of everything, which I think is exciting. So that was one question, and the other one is, should we start growing and shrinking your memory maps? You know, a bit like if you look at growing and shrinking neural networks, why don't we do that on the data as well and go on with core sets and not just one single core set, but we have dynamic core sets. So yeah, you see, just
both are great suggestions. So yeah, we've looked into a little bit in non-parametrics, but it's related to Gaussian process right now. So I haven't looked into gradient boosting, but you're right, there should be definitely a relationship. And also the memory map, like we have only shown that memory map looks like this. It has some characteristics, but we have not used it to change the training of how the model learns. But that's really what we want to do in the future.
So one more.
Yeah, super interesting. I'm curious, haven't you just presented a pretty powerful way of creating disruption as well? I mean, in terms of, you know, the data points that you really want to manipulate or maybe inject in order to maybe for nefarious purposes? Or should we not be concerned about that?
We should be very concerned, right? So yeah, I completely agree. So we should be very concerned even now because people can do all sorts of things with your model, but we don't know right now why somebody can do something. So I think understanding is very important of what we're making. So if we understand why some things are working, we at least know how to protect them, safeguard them. But if you think that everything is magic, then you know what are you going to do? So I hope that this work will not disrupt things, and I would really like to work towards that.
Cool. Looking forward to discussing more.
Thank you.
So then let's thank our speaker again. It was awesome.
Thank you.